Over to you, Gina.
We're going to be talking about simplified energy calculations for lifts. You've had a number of sort of tutorial type presentations over the period of these 2 days. This is a similar one, and what we're going to present is a way of simply making an energy calculation for lifts. I'm going to do the first part. Anna's going to do the section concerned with some examples, and then I'm going to sum up at the end of it. It's often necessary to try and select the best performing lift installation in terms of energy, particularly if you've got to gain the first credit from BREEAM. And although there are some methods of calculation available, there's one in CIBSE 2010, they're pretty inaccurate, and they don't give you a proper indication of the energy use that you might have. Fortunately, the ISO group, WG10, started to develop a calculation method, and with the work that Anna did for her PhD, which has enabled us to produce a number of tables which simplify the calculations and allow you to be able to calculate a more accurate energy take for either a system you have or a system you're going to have. Now, I said this is going to be kind of a bit of a tutorial. For instance, if I say to you, if you want to calculate the length of the hypotenuse on a right-angled triangle, you just say a squared plus b squared equals c squared, and you don't actually go through some sort of calculation, some sort of proof of that, you accept it. Pythagoras did it donkeys years ago, and there's about 20 different proofs. If you go on Google and go Pythagoras' theorem, you'll find there's about 20 different proofs of Pythagoras'. So I think we can accept Pythagoras. Now, it doesn't mean to say that you can accept this simplified method, but for the moment, accept it. Right, so let's have a look at how you would want to calculate energy consumption. We've got three data sets. We've got known data. I sound a bit like Rumsfeld, don't I, with his known knowns and his unknown knowns and his all that lot. But we've got known data. We know what the rated speed, rated load, acceleration, jerk, terminal to terminal floor distances, all those things. They're physical things. They are known data. We have to measure some data, and some of the data that we would be measuring would be trying to get the energy consumption for the ISO reference cycle. We get that. If we don't actually have it, we may be able to get it from simulation. We've talked a lot about calculation and simulation here over the last 2 days. We may not have an actual value from a model lift, but we could perhaps get it from a simulation. Then we come to the tricky bit. We come to the estimated data. And that is an indication of the activity of the installation, which might be ranging from very low activity to very high activity. And this is represented by the number of trips per day. Now, the energy consumption, the daily energy consumption, is two parts. That's the daily consumption, which is made of two parts, which is when it's running about, doing things, moving people about, maybe parking, that sort of stuff, and when it's standing. And the standing part has got two parts as well, when it's idle and available to go, and when it may be in standby. So the daily energy consumption is the sum of those two parts. Now, what we need to do is to evaluate those two parts. First of all, if we look at the daily running energy consumption, this can be determined by this formula here. It's a very simple formula, not like a lot we've seen here over the last 2 days. It is simply the number of trips you make, multiplied by the distance you travelled, multiplied by some factor to represent the load in the car, multiplied by the ISO reference cycle energy. Now, if we need to be able to evaluate all those numbers. And what we need to do, first of all, is just have a quick interlude in what the ISO reference trip is. The ISO reference trip, and it's according to it's BSEN ISO 2745-1 2012, and it is the measuring of the energy taken by taking a lift car from one terminal floor through to the far terminal floor, opening and shutting the doors, coming back down to the first terminal floor, opening and shutting doors, and measuring that energy. Very, very easy to do. No weights to take about and shove in the car. Just simply run the thing several times, divide by the number of times, and that gives you the energy used in the ISO reference trip. And that was one part of that equation that I showed you just now. But we now need to know the travel distance and the load typically that the lift would be carrying and travelling. In the early days, I used to just say, well, the travel distance is about half the distance between the terminal floors, you know, including basements and all that, and the average load is 0. Most lift cars, except during peak, don't have many people in them. It runs around at very low values of load. But that wasn't really good enough for the ISO work, and so by doing many simulations that Anna did, we were able to develop some tables to give us those values. Now, I do suggest that you might want to have open the printed copies of the paper, because I'm going to flit about amongst these tables, and you might want to just look at them as we go through. Now, the first thing is to determine the number of trips per day for the target installation. And this is a matter of opinion or a matter of knowledge. If you have an existing system, you may have a trip counter on it, so you know what the number is. If you haven't, then maybe the owner or the tenant or whatever might know what their usage intensity is going to be. And table 1 in the paper gives you 5 usage categories. And those 5 usage categories go from very low to very high, and they're represented by median values of the number of trips per day, running from 50 at the low level, sort of thing you might have in a small apartment building, to very high, where you might have some headquarters building, prestige building, with an intensity of traffic. The ISO standard does have a category 6 as well, which is more than 2,000 trips per day, and that was put in because Asian countries say that they do have lifts that are taking that number of trips per day. Perhaps in Europe and other places we don't get those high levels. So the first thing is we need to be able to categorize the number of starts that the lift is going to take per day. We may know it, we may guess it. Having got that, then we need to know what the percentage average travel distance is going to be, percent S, which is the travel distance for the average trip of those number of trips per day. And that can be taken from table 2 in the ISO standard. This ISO standard, by the way, is out as for comment at the moment. The comments have to be in by 11th of October. So if you want to get it off the BS website, you can do, then appropriately comment on its contents. Table 2 in there gives us the percentage average travel distance for the different categories and for the number of stops that the lift might make. Obviously, 2 stop is the minimum number of stops a lift could make, otherwise it's a room. 3 is interesting because sometimes one of the floors is just a little bit different from the other one, maybe a meter or something, because it goes through to a loading bay or something of that sort. But then we have greater than 3, which is typical of the lift installations we're going to come across. And the work that Anna did determined that for users categories 1 to 4, the lift travelled on average 44% of the distance between the terminal floors, near half. But as you got up to the higher intensity of travels, then it only ran a third of the distance. So that's average distance travelled. Now we need to know what the average car load is. How many passengers are we moving around in that lift over the course of a day? In general, the average loading is low. We know that we've been talking about calculations the size of the lift to deal with high numbers of people. And clearly, if we could load the cars all the time at balance, 50% or whatever it is, 40%, if all the cars could be arranged to run around at a balanced value, the energy take would be lower than if they're empty. Because if they're empty, we're hauling the counterweight around, so we're moving this out of balance energy. But however, it is low, which is against us in saving energy. So we need to correct the value that the ISO reference cycle gave us, because that was done with an empty car. We have to find out what the energy might be if it wasn't empty. And it's actually going to make it smaller for traction lifts and more for hydraulic lifts. And so here we have a table, table 3 in the book from ISO, which indicates the usage category and the percentage of rated load which is being taken by the car on average across the day. And you can see it's related to the rated load. It comes into 4 categories of rated load. And you can see it runs from 2% for a very large car just going 3 floors to quite a large number of a small car within some intense duty. So that's taken care of the average car load, but we do need to correct it with this load factor in the equation. This table just simply tells us what it is, but we have to apply a correction factor to that equation, the first equation I mentioned, which is KL, and that's dependent on the value that was in the previous table, and it also is dependent on the balance, and we've shown here 2 different balance values for traction lifts, 40% and 50%, and we've shown some values for hydraulic lifts, no counterbalancing, some counterbalancing, a lot of counterbalancing. Counterbalance hydraulic lifts are quite rare, but we put them in because sometimes they do exist. You'll notice that the values that you get on traction lifts are less than 1, which indicates that the more load you put in the car up to balance value is reducing the energy that you're going to take. But you'll notice that they're greater than 1 on hydraulic lifts, because the more people you put in, the more people you've got to move up and down with the car. So that's the value of KL. So the first 3 equations that I've got on there are for traction and hydraulic lifts. Now, that's the running energy. But we also have the energy when the lift is standing. And we say standing, and maybe here we ought to say upright, was it? Whatever, rather than standing, but it's standing. And the standing has got 2 components. It's got a component for when it's idle. In other words, it's just got to a landing, it's opened its doors, it's let the passengers out, it's closed its doors, it's got nothing more to do, it's just standing there with no demand. That's idle. If it waits long enough, it should get into standby. And in the ISO standard part 1, it suggested that there should be 2 levels of standby, a 5-minute one and a 30-minute one. In my view, the 30-minute one is too long. If you're using a kilowatt in standby for idle for 30 minutes, that's a lot of energy loss. They should get rid of it in 5 minutes. And so what we need to do is to calculate the amount of energy that's being used while the lift is actually not moving people about. And there's a ratio between the idle and the standby in that period of time of standing. To get that energy, we need to find out how much time the lift is standing, and that's 24 hours minus the number of trips it's taken times the amount of time it runs along those trips. That's given by this average time here. That's the time that the lift is standing, and then that's the 2 values of energy take that you've got when it is standing. Now, those values also have a ratio, depending what the traffic intensity might be. If you've got a low intensity traffic demand, then the idle is small and the standby is larger, but you'll see that it changes up here to bigger values, more equal values, if you've got an intense traffic situation. So that's table 4. So we could put those pieces of information into our equation and calculate the energy take.
How can I change the page?
Just pull that down gently.
Hi. So I've got a very difficult task to apply this formula, which you've seen is very simple. So, sorry, yeah, it's true. Yeah. Shall I repeat? First, I would like to remark that there are a bit more changes in this paper related to the ISO standard, because ISO standard requests 2 measurements, and here we just do 1, and we apply a coefficient to take into account that the distance is different. So ISO is a bit more complicated, trying to gain accuracy. So in this example 1, so we take a lift from the Swiss Federal Office of Energy. It's published in the web page you can find there. And as Gina says, we can have some lift parameters given. We know what is the rated load, we know what is the rated speed, trouble, and number of stops, and also what is the counterbalancing. In this case, because it was not in the publication, we don't know what acceleration and jerk are, neither the door times, but we imagine them just for the example. So we take them from tables. So we have 1 meter per second squared and 1,25 for jerk. And we estimate that the door opening times are 2 seconds, 2 seconds for closings, and because it happens twice in the ISO reference cycles, we have 8 seconds during the trip. Then we take some measurements. For a consultant, this parameter or this data can be given by lift manufacturers. So we need to know the ISO reference cycle, which in this case is the energy consumption, which is 170 watts per hour. We need the idle power, which in this case we didn't know either from this web page, but we estimate that it is, for example, 500 watt. In some lists of lifts with energy consumption of lifts, we find such values. And we estimate, or we have that the standby power is 120 watts. If we have no clue what will happen with our lift, we can estimate it will be the highest usage category, so that would be number 5. So if you go to the table, you will see the average value in the table is 1,500 daily trips. And if we go to the next table, to table 2, we see that for category 5, we have a 33% average travel distance. If we look for the average load, we will have a 7% because we have different values for the different car capacities. And in our case, we have a 1,600 kilogram car, so we will have a 7% average load. I also want to remark here, ISO has gone for simplicity, so the tables are very, very much simplified. So we could extend them some more, as we will see later on. They wanted it to be very simple. The load factor can be calculated according to the formula that Gina has shown previously, which is also in that paper. We just need to take this 7%, which is the average load, and multiply by that coefficient and subtract that from 1, so we get 0,89. And we take from the last table, from table number 4, the ratio between idle and standby. I also want to remark here that this ratio is considering the full day. So if we just consider operational time, they are different. Next page. So we just need to apply the formula. We say the running energy will be the number of starts that I have, which in this case is 1,500 times the average distance traveled, which is 0.33. The load factor in this case is 0.89. And the energy consumed in the round trip is 170, and we have to divide by 2 because the round trip is up and down, and each trip is just once. So in one round trip we have 2. So the running energy consumption will be 37.4 kilowatts, And for the calculation of the standing energy, we first need to know how long we are standing, or because we have ratios. So we first need to know what is the time the lift will be standing. And to know that, we have to subtract that from the time running. And the time running, we can get it from the average distance, which is 0.33% of the building height. So if we multiply by the building height, we have the average travel distance will be 25 meters. And if we apply the formula available in the CIPSI guide, dividing the average distance by the speed, and then the speed by acceleration and acceleration by jerk, plus the time that we will be opening and closing doors, because according to ISO, this is included in the round trip cycle, we will have that the car is running 21.3% in average. So if we divide that, if we multiply that by the number of times that we are having this trip, so the number of starts, and we divide by 3,600 to get that in hours, we get the number of hours that the lift will be standing. And multiplying by the power in idle and standing, we will get 4.2 kilowatts per hour. So the daily energy consumption will be the sum of both, and we will get that this lift will be consuming 42 kilowatts per day. But as I said, ISO has tried to be very simple, so we have given just 5 categories, 5 uses categories, and median values. So, but the uses category number 5 goes from 1,000 trips to 2,000 trips. So the question is, what is the error I'm making if I'm considering this average value instead of going to the real number of starts? Because as Gina said, it is also allowed that if you know the number of trips that your lift is going to do, that you use your own numbers.
Okay.
Okay. You should just see one of the pages, but it's okay. It's a problem of word. So this is the curves from which the data of the ISO, from which the data were taken for ISO. And this is showing the average distance traveled by the lift depending on the number of starts, because it was the consensus of the sector that the parameter which is better known by the lift consultants is the number of starts, or the most probable number of starts. So I made many simulations, and we got the average curve. The other points correspond to other lifts. I could be more precise. I can show these curves for different combination of parameters, but it is the average. And the average of the average is for 1,500 starts, I get this 33% average distance. But as you see, if I take the number for 1,000 from this average curve, I have more. So I have 42%. And if I go to the other part of the range, I will have 28. So we see that the average distance is decreasing with the number of starts. If I go to the table of the average load, I think the quality is a bit bad. Do you see the points? More or less. Okay.
The points are clear.
Okay. So this graph is showing the average load. Again, depending on the number of starts, and because ISO wanted to do it as percentage of the car capacity, and in fact this parameter can be counted as passengers, but if we take into account the capacity of the car and we divide passengers by capacity, we need more than 1 curves. So in this case, we have 4 curves for different car capacities, and in our case we have, sorry, not 4, 5. We have to take not the lowest one, the one above. And we see for the standard, we took the average value for 1,500, which is 7%. But if I have less starts, I have less average load. And if I travel more, I have a higher load. So in this case, if I want to be more precise, I have to consider 4 for 1,000 trips and 13 for 2,000 trips. For for idle and standby, the graph you have in the paper corresponds to the operational time. But this is taking into account all of the day. So for producing the ISO tables, we also made some estimations to see what can happen the rest of the day, because the traffic patterns do not consider them. So the values were extrapolated to these other curves. And if we see for very low usage, we have very high standby, very high. Standby and very low idle, and they approximate with the number of starts. And again, for 1,500, I have in the ISO table, I have 42 and 58. So 42 would be idle and 58 will be standby. But I see if I go a bit lower to 1,000, or if I go a bit higher, then the number is more or less the same. So up to 1,000, or previously they stabilize. So if I go to my formulas and I put them in a table, now my data have changed. So I have, instead of 33, I have 42 and 28. As I said, we see that the average distance descends with the number of starts. We also see that the average load increases. Because the average load increases, the load factor decreases. Gina has already explained why. And the ratios, either idle, standby, they also follow attendance, although in this case they are quite similar. So we have we reduce from 45 to 40 in idle, and we increase from 55 to 60 in standby. So if we apply the formula to calculate the running energy consumption, we have an increase, but in the first case we increase 2.3 kilowatts, and in the last case it remains more or less the same. But if we look at the standing energy consumption, we have a bit higher difference. But at the end, I have to sum up both, and I get that the energy consumption more or less remains the same. So in this case, the error I would have made if I take this average value would be very low. So we could say that the tables are quite accurate. But this is very much depending on what are the different values between idle and standby, because I have different ratios. So if this power consumption differs a lot, they might not compensate, or I might find another attendance. And the same occurs with the travel distance, because energy consumption during running depends on travel distance and also on the number of starts. So they can compensate each other. So I cannot take any conclusions just for this case, for this concrete elevator, where I have all the power consumption numbers and where I have my energy running cycle. And Gina, I think you wanted to. No, this was yours.
Okay, it's mine.
Yeah.
Okay, the conclusions then on this are that we have our average travel distance diminishing as we increase the number of starts. The average car load is increasing as we increase the number of trips. The load factor diminishes because we're helping reduce the energy by getting close to balance. The idle standby does change, but not significantly. And we end up with a set of numbers which are 42 kilowatt hours, which is about 0.4p per trip of the lift makes, or 0.4 of a cent, whatever. It's not much. And the range in this particular case is only a few percent. But you will remember on the graphs that we were looking at further back here, that if you were to be working down at the very low levels, we picked a usage category at the high levels. There's a significant change here in the distance travelled. There's quite a significant change down here for the load transported, and if you're down at this level here, then you can see that these are not as level as they are in the higher levels of starts. So we've picked an example perhaps which is a bad example because nothing much has happened, but if you were taking one of the lower usage categories, you might find a complete change if you accepted the median value. So some conclusions. This calculation method considers both standby and idle in standing time. Some previous calculation methods have only considered standby. they didn't distinguish between standby and idle, and there is a difference in energy consumption. The calculation method doesn't cater for double-deck systems, it doesn't cater for running through express zones, it doesn't cater for unequal floor heights, it doesn't account for unequal floor populations, and it only considers very simple control systems. The ISO work is on the basis of a single unit. That's both for part 1 and for part 2. It only considers a single unit. The working group considered it to be too complicated to consider the different traffic control algorithms as an influencing factor. So they will have an influencing factor. Obviously you can create an algorithm which gives you an optimal energy take, but it's not considered. It's just simply a single unit is being considered. The energy simulation is more accurate than a calculation method, but only if you know the building data and if you know the usage demand. Otherwise, the calculation method gives you a very quick, like a round-trip time equation, it gives you a very quick estimate of energy take. This paper doesn't show how all these tables were developed. We did present a paper last year on how the tables were produced by doing all the many simulations with many different installations to create these tables, and I will refer you back to that paper. And eventually Anna will be publishing her thesis, which is several hundred pages long, so if you really want to know where they all come from, it will send you to sleep at nights, because it's done that to me several times. This method that I've presented provides the most accurate estimation of energy usage available today in public and private domains, and I challenge you to find me a better one. Thank you.